Well. Let's get going, everybody. How's it going? Test. There we go. Okay. No. Let's make sure I'm actually picking up audio. There. Test. Okay. Whoa. There we go. Maybe? No? Huh? Something? Gotta press the gain button. Increase the gain. Something. There we go. Maybe? Yeah? Okay. Cool. All right. Hopefully I'm coming through all right there. So anyways, welcome back after a long weekend. Hope everyone's doing super good. Another day of proofs. Another day of set theory. Another day of logic. Let's do it. By the way, how many of you guys, do you feel that the course title, which is listed in the computer as proof, set theory, and logic, how many of you feel that it should be this? Because I feel, I don't know, I have strong feelings about it, but that's neither here nor there. Okay, I don't know, whatever. Anyways, we're back to it. Last time, we proved that the square root of 2 is irrational. Today, we will, among other things, end up talking about whether the square root of 2 to the power of the square root of 2 is irrational. Who knows? That might come up in a proof we do. A good question, a hard question, an interesting one. But first, we're going to talk about proof by cases. So we are in section 2.2.4. Proof by cases. So one of the harder homework problems in the next assignment is the following. To prove the implication P implies Q via cases, we make use of the following argument. You will prove this in your homework. You will show that P implies R or S, and R implies Q, and S implies Q, tells us that P then implies Q. That is, proof by cases boils down to the following. It says, hey, if you've got something, then two possibilities. Each of those possibilities implies your desired conclusion. Therefore, your initial thing implies the desired conclusion. Does that make sense? Okay. You will struggle with this one on the homework. It is a tough one. I have many good tips for you. There are lots of different ways to go about this. There's always the brute force truth table way, a boring way to do it, but a way to do it nonetheless. I recommend perhaps converting things to contrapositives. May make life easier. I perhaps also recommend using the disjunctive form of an implication. That may be helpful as well. Two good hints. We'll see how it goes. Give it a shot. I want you to struggle on this one because proving a seemingly obvious statement like this in a formal way is harder than you think and is a good way to get your math muscles flexing. I don't know, right? It's a good workout, mentally speaking. So fun. Enjoy it. But basically, the idea of proof by cases boils down to, and notice you could expand this type of argument to have very many or statements here as long as you had equally many implications afterwards. Basically, all it boils down to is saying, hey, you got something? Well, there's a couple of options. Each of those options implies my desired conclusion. Therefore, the thing I originally had implies my desired conclusion. Does that make some sense? Okay. In a standard proof, we will write these out as cases. That is, R is one case and S is another case. Usually, these will be mutually exclusive cases, but I want to point out that they need not be mutually exclusive. That is, this is not an exclusive OR. This is an inclusive OR, and it's still fine, right? There could be overlap between the cases. However, all you have to do is essentially show that the first thing falls into one of these cases, maybe both of them, something like that, but that no matter which case it falls into, you get your desired conclusion. Let's do an example here quick. So prove the following theorem. Theorem, if x is a real number, then x squared is greater than or equal to 0. A seemingly obvious statement. How do we go about proving it? Well, let's start. What can we do? I would say the easiest thing to do to start is to split everything into two cases. So we'd say something like, let x be a real number. Then either x is greater than or equal to 0, or x is less than 0. Do you agree with that? Okay. We proceed by cases. This is a kind of a convenience to the reader, saying something like this, right? Just like saying, like, we prove this via way of contradiction, or something like that. You're letting the reader know the proof style that you're going to employ. Okay, case 1. Suppose x is greater than or equal to 0. Okay, basically what we said is, look, let x be a real number. This implies that either x is greater than or equal to 0, or x is less than 0. Now we'll show the greater than or equal to 0 case implies that x squared is greater than or equal to 0. And then we'll show that the less than 0 case implies x squared is greater than or equal to 0. Therefore, this thing, right? Okay, so suppose x squared is greater than 0. Then x squared, well, that's equal to x times x, which is greater than or equal to x times 0, which is equal to 0. Do you agree with this statement? Yeah? Perhaps? That is, I just multiplied both sides of the inequality by x, noting here that multiplying both sides of an inequality by a positive number preserves the inequality, right? Or at least by a non-negative number. It certainly doesn't mess it up, yeah? Okay, cool. Do you agree with this? I'm seeing some looks that say, I don't know about that one. Perhaps what you're feeling is this sort of sense of like, hey, how do we know how inequalities work? And you're right, we are kind of brushing that detail under the rug here. And if we wanted to be very, very formal, we should start by showing that we know how inequalities work, that multiplying by a non-negative number preserves an inequality of this form, the less than or equal to variety, yeah. But we're going to essentially brush that under the rug for right now, since the purpose of this is to illustrate how proof by cases work. And we haven't built up from foundations yet, which we will start to do once we get into set theory. So we'll get to these sorts of foundational concerns soon enough. But does everyone feel all right about this first case? Just, using your basic knowledge from algebra? All right, let's do case 2. Suppose x is less than 0. Then x squared, which is equal to x times x, is greater than x times 0, which notice is equal to 0. Same logic, but now we're just using the fact that multiplying by a negative number reverses the sign of the direction of an inequality, right? Does everyone remember this business with multiplying by negatives, flipping inequalities? 1 is less than 2, but minus 1 is bigger than minus 2, right? If you owe someone minus $2, you are more in the hole than if you owe them $1, right? Or sorry, if you owe them not minus 2. If you owe them $2, you owe them more money than if you owe them $1, right? Yeah, there you go. Everyone gets the idea. Okay, cool. Okay, but we should be clear. So it is certainly true that x squared is greater than or equal to 0. That is, we showed that x squared is greater than 0. We should be careful to notice that that is not the statement we actually wanted to prove at the end of the day. What we wanted to show is that x squared is greater than or equal to 0. So we should be clear that having x squared bigger than 0 does indeed imply that it is greater than or equal to 0. Right? OK, fine, fine. Yes?
Why does the inequality flip when why is the x's not negative?
What?
Why are the x's not negative?
They are negative. X is less than 0, right? So it's negative. And when you multiply the things by, multiply an inequality by a negative number, it flips, right?
Yeah.
Like 2 is less than 4, but minus 2 is greater than minus 4.
Yeah.
Yeah?
So we're saying that in case 2 here, that x is negative based off the implication that x is less than 0. That's
Yeah, this is why it flips. Starting from right here. Yeah. Okay. Yeah. I guess I'm just implicitly using our knowledge of algebra in this manipulation right here. And like I said, if you wanted to proceed from first principles, you should show that this is indeed how an inequality works with the real numbers, that when you multiply by a negative, it flips. And you should use that to justify this step. However, here we're just kind of taking the basic kind of algebra piece right there as a given.
X is implicitly negative.
It's not even implicit. It's explicitly said to be negative. Yeah, indeed. Negative just means less than 0, right? Yeah. Great question. Right on. Cool. Feeling good about that? Yeah? OK. Cool. So we may conclude, in either case, we have shown that x squared is greater than 0. Therefore, our conclusion, if x is a real number, x squared is greater than or equal to 0. What do you think of that? Now notice, while we initially split it into 2 mutually exclusive cases, they did not have to actually be exclusive. That is, when we say either this or this, it could be the case that perhaps both could be true, in which case it doesn't matter which argument you use. That is, if we had said instead of x is greater than or equal to 0 or x is less than 0, what if we had done less than or equal to? Would anything really have broken? No, we just wouldn't have needed this line. Either way, it still works. That is, this or right here is not an exclusive or. It is totally fine to do this. Does that make some sense? I think everyone has this implicit idea of proof by cases as requiring you to take a possibility and split it into a bunch of distinct sub-possibilities. You can do this. This is totally reasonable. You can partition your space of possibilities up. But it's also totally fine if there's some overlap, as long as it covers everything. Yeah? Cool. OK. Nice. So fair enough. Proof by cases. What do you think? I think proof by cases is actually one of the easiest proof techniques. People feel comfortable with it implicitly because it makes some sense. Yeah? Or, I mean, maybe that's not a good explanation. But I think people reason like this very often by trying to break things down into simpler parts. So, OK, cool. Proof by cases. How about it? Nice. Now, proof by cases is not so bad, but we have a few more other techniques that we may want to employ here and there. For instance, we may want to prove quantified statements. So this is section 2.3. Proving quantified statements. So what about universal implications? Oh, I'll use this as its own little section. Or not universal implications. Universal, jumping ahead of myself. quantifiers. Universally quantified predicates is what I'll say, since I'm stumbling over my words on this Monday mid-morning. So here's the idea for a universally quantified predicate statement that you want to prove. So in this case, good, I have switched my camera. Here's the idea. So in general, proving a universally quantified statement has the form of showing something, or I'll say showing for all x, p of x is true. Yeah? Showing that, hey, for whatever you take, the predicate is true. Yeah? Okay. Notice this can be recast as an implication. So specifically, if x is in the domain, then p of x. Does that make sense? Oh, okay. So you can think of a universally quantified statement that you want to prove as an implication. So this is the basic proof technique. Take, if I can write clearly, take an arbitrary element of the domain and show the predicate is true for this element, i.e. when you instantiate at that particular value, right? That is, you say, like, you want to show something is true for, say, for instance, a real number like we just did. You say, like, let x be a real number. You pick one, but without saying which one, right? And then you show that it holds. Okay, fine, good enough. Therefore, since it didn't matter which one you picked, and you showed that it held for the one you did pick, not saying which it is, it holds for any one, right? Does that make some sense? Okay, I don't know. Hopefully that does. But I think that in general, proving universally quantified statements is not so bad. Effectively, it's what we were just doing. That is, when we said, if x is a real number, then x squared is greater than or equal to 0. An equivalent way of saying this is for all real numbers x, x squared is greater than or equal to 0. That is, we've kind of been doing this very frequently for the last couple of days in basically every other one we've done. What do you think? Yeah? Now what about existentially quantified statements? Yeah? What about that? So, existentially, quantified predicates are usually proved in a slightly different way. The idea is to construct an example in some form. So here is an easy example to show what I mean. So here's the idea. Prove the following. So let's prove the following theorem. The theorem is there exists, or there is, a positive integer n such that n plus 1, n plus 2, n plus 3, and n plus 4 are all composite, i.e. not prime. Now, what could we do here? How could we show this is the case? Perhaps this seems like a really complicated statement, right? Do you think it's going to be really complicated? No? Who's got an idea? How could we go about it? What do you think?
Choose a value that satisfies this statement.
Exactly. We're only making a statement that there is some choice of n. So to show that there is, you could just find one, right? If you're like, there's a dog named Rex, and you're like, proof, here's my dog, his name's Rex, right? You've shown the statement's true. You could also, do something more complicated, right? By, filtering the database of all dog names for every entry except Rex, and then showing that it's non-empty or something like that, right? Silly compared to constructing a specific example, yeah? Existentially quantified predicates are best addressed, if possible, by constructing a particular example. It tells you the most about what's going on in some sense. So let's try it. Okay. What number would you pick? How would you do this? What do you think? 24? Oh, an interesting choice. So let n equal 24. Then n is 24, and all that we have to show that it's composite is to show that it has a divisor other than 1 in itself. So I'll just write this as 2 and 12. n plus 1, that's 25. That's 5 times 5. n plus 2, that's 26. That is 13 times 2. n plus 3, that's 27. That's 9 times 3. And n plus 4, that's 28. That is, well, 14 times 2. Oh, okay, cool. So such a number exists. How did you go about finding that number?
I thought about it as like primes, interval between them. So 23 is a prime, right?
Okay.
The next prime is farther away, so it would work.
Oh, well, that's a very interesting way of going about it that I would have not have guessed most people would have employed, is saying that the gap between primes grows larger, so you just went far enough in the sequence to have enough room. I guess that's reasonable. Yeah, although it's actually unclear whether or not the gap between primes grows larger. There may be infinitely many primes with very small gaps, right? In fact, people think that's probably true. But it's yes, no, right on, right on. There are other ways to do it as well. You could, do some business with factorials, right? Something like that, yeah? Perhaps. What do you think? Yeah, I don't know. So there's many different options. So you could do something like you could pick, I won't even go too far into it. But suffice to say, I don't want to construct a general case and make this seem like I'm now trying to prove an entirely different statement. All we had to do is find one example, and we did find one. So it shows that we're good to go. What do you think? Feel reasonable? Okay. Now, do you always have to do this? That is, do you always have to actually explicitly find one? Let me show you a weird thing that you can do sometimes. So I'll go and do a quick little bit of erasing right here. And you get started trying to prove theorem 2.24 in your note packet, which is the one you prove in example 2.23. Okay, so I gave you a moment to try to prove this. The statement of the theorem we're about to prove says that there exist irrational numbers a and b such that a to the b is rational. An interesting claim, right? Weird. A number you can't write as a fraction to a power of another number you can't write as a fraction. But the result is a fraction. Huh, what do you think? How can we go about showing this? I would start by picking the only irrational number we certainly know at this point. Yeah? Square root of 2? Yeah? Okay. So, to begin, we will say the following. So, observe that we have square root of 2 to the square root of 2 to the square root of 2. This is equal to the square root of 2 to the power of the square root of 2 times the square root of 2. Do you agree with that? And this is in fact equal to the square root of 2 squared, which is equal to 2. Yeah? I'm going to put everything together right now. This is fun. So it looks like we're done, almost, but we have to be careful of something. I don't know if the square root of 2 to the power of the square root of 2 is rational or irrational. Do you? Off the top of my head, I don't know. I don't remember. Okay. So, do we need to know?
Because there are cases.
What if we did cases? Yeah. We proceed by cases. Case 1. If square root of 2 to the power of square root of 2 is rational, we are done, since square root of 2 is not rational. That is, if the square root of 2 to the power of the square root of 2 is rational, well then certainly I've got an irrational to the power of an irrational that is rational, which is what we wanted to show. So either this is a perfectly fine example, or case 2. If the square root of 2 to the power of the square root of 2 is not rational, then the square root of 2 to the power of the square root of 2 is an irrational number. And if I raise it to the power of the square root of 2, that is an irrational to an irrational power, and we get something that is rational, and we are also done. Therefore, the statement holds irrespective of whether or not square root of 2 to the power of square root of 2 is rational. Huh. Interesting. If it is rational, then bada boom, you're already done. If it isn't, well then bada boom, you're done. That's a weird one, right? It doesn't matter whether it is or isn't. You don't even need to know. So, notice we proved an existential statement without actually coming up with a specific example. That's weird, isn't it? Perhaps, but perhaps not. That is, there are plenty of situations like this that you can Oh, okay, so I mean, like I gave like that example with dog names or something like that, right? You can imagine many other examples like that where you go, okay, like show this, right? And then instead of directly showing it, you show somehow something that would imply that were it not the case, then this would not make sense, right? Like for instance, if I, let me think of a good example. If I made the claim, I'm trying to think of something that's relatively distinct from the last example I made, but it will be ultimately kind of a similar instance since I'm making the same point. But if I said something like, oh, if I was like, you know, like, there exists a day I went for a run last year. Oh yeah? Well, here's my calendar. Here's all the days I didn't go for a run. Is it the whole year? It's not? Okay, then there must have been a day I went for a run, right? I didn't tell you which day I did, right? But I gave you a list of ones that I didn't, and that's all the ones I didn't. So, you know, if it's not the whole year, then I must have done it one of the other days, right? Okay, so there's many examples like this, right? Where effectively you produce a proof of an existential statement by supposing that there isn't and then showing that that leads to something impossible, right? For instance, the year having fewer days than you know it actually has, or something like that, right? Do you get what I'm saying? Okay, I think everyone gets that bit. But there are other more interesting ones where you can show that, like, okay, well, if there is such a thing, then some cases, and in either case, you get your desired result. And so you don't have to actually know whether or not, like which case holds, right? That's kind of a weird one. But this thing pops up. All right. Now, closely related, effectively kind of the same business, are counterexamples. Counterexamples are all about disproving statements. So disproving a statement is proving the not of the statement, right? Here is an example. Disprove the following conjecture. Here's the conjecture. All integers are even. Or actually, did I say, yeah, every integer is even. Yeah, all integers are even. What would your disproof be? Your unproof? Yeah?
Give him an odd integer.
Yeah, exactly. Right on. So you want to show that this statement is false. So what you want to do is prove the not of this statement. So I'll write this as a disproof, not proof. We prove that not all integers are even. That is, we show there exists an odd integer. We do so by producing one. Yeah? To do so, consider the integer n equals 1. Yeah? And whatever odd number you want. Yeah? N equals 1, which is not even. Or we could even go through and try to appeal to something from a previous one, or one of these statements we've proved about evenness and oddness from before. But as long as you accept that 1 is indeed not an even integer, hey, look, we just proved it. Yeah? So counterexamples are just to show a counterexample, you show a proof of not the statement, right? That is, you prove a existential version of it, yeah?
Is it always that simple that you just like use literally just a number like that, or are there certain instances where you have to actually give a proof that we already know?
Oh, it's okay. The question here is a good one. The question is whether or not it's always this simple, or if sometimes you actually have to do something harder. And the answer is that yes, sometimes you definitely have to do things that are harder. There are plenty of conjectures that people maybe suspect are false or have suspected are false that have either eluded disproof for a long time or did elude disproof for a long time and eventually were disproved, but through titanically complicated means. Indeed, it can be very hard to show that something is not true, right? Were it the case that you were able to show things were not true very easily, then any statement that you wanted to show was true, you could just show not that statement, right? So it is effectively of the same level of difficulty in some sense. The nice thing, though, is that notice this was a statement about all integers. To disprove it, we only had to find one thing that was a counterexample. Now, if on the other hand, we had an existentially quantified statement, and we wanted to disprove it, then we'd have to prove, or not, if we had an existentially quantified statement and we wanted to disprove it, we would have to show that not the statement held for all values, right? We'd have a universally quantified statement to show, which you can't show by picking a particular value. Fair enough. Okay. What do you think? Counterexamples, not too crazy. By the way, on the subject of showing a thing is not true, something I have run into a strange amount of times in math in various classes is people who are somehow have been told for some reason that you can't prove a negative. Have people said this to you for some reason? No? Some people have nodded yes. Okay. Just in case you're one of the people who said you can't prove a negative, here is my counterpoint to that. I don't know who told you this. I guess people are proceeding from the empirical claim or something like that you're, only able to fail to support your desired conclusion as opposed to disproving it or something. But we're not making empirical statements here, right? But people who say you can't, if you say you can't prove a negative, I would say, oh yeah, well, you can't not prove a negative would be then a statement that you could not prove, so you wouldn't know this, right? You get what I'm saying? Yeah? Maybe, maybe not. I don't know. I always find it funny. I've encountered that several times where people have been very upset and confused by things where they go well, I've been told you can't prove a negative, and now you're telling me to prove not this? That's impossible. But people are taking things from the empirical sciences and acting like they apply in other situations when they perhaps do not. But, all right. So counterexamples, almost a footnote. They're easy. Just show that it's not the case by producing an example of it not being the case, or perhaps, I guess it's the counterexample, while the counter to an existentially quantified claim is usually more difficult. Okay, fair enough. And this brings us to perhaps the most fun part of this, which, we are relatively close to the end. Well, up next, we're going to talk about mathematical induction. I won't actually do it today. We'll leave this for its own full topic, so I don't have to just rephrase things a lot of times. However, for a basic idea of it, how many people have seen induction before? Most of the room raises their hand. Okay, well in that case, the easy way to think of it is induction is like climbing a ladder. Yeah? Induction says that if you can get on the bottom rung, and if being on one rung lets you get to the next rung, and you can get to any rung you want, right? You need both of those things. If getting on one rung lets you get to the next rung of the ladder, you still need to get on the ladder in the first place to be able to get to the top, right? So, okay, you need both pieces. You need to show that there is a case where it holds, and then having it hold for one case means it holds for the next. We'll write this out formally next time, and we'll talk about everyone's favorite, least favorite style of proof, one of the two. People either like induction or they hate it and find it confusing. We will do plenty of induction in this class. It will happen quite a lot. So, next time, Mathematical induction. I'll see you around.